Okay, I am Jérôme Juillard from the Gibbs lab located in the center of Universiteit Paris-Saclay, talking about output metrics for amplitude-modulated resonant sensors based on weakly coupled resonators. This work is part of the ongoing PhD of Ali Mostafa, who's co-supervised by me and Pietro Ferreira, and of Manon Gouspy, who's in joint supervision with Michael Kraft from KU Leuven. I will first introduce the context and background knowledge of our contribution, starting from frequency-modulated resonant sensors to phase and amplitude-modulated resonant sensors based on weakly coupled resonators. Now, amplitude-modulated sensors face the bottleneck of analog-to-digital conversion. We'll see how using a ratiometric delta sigma analog-to-digital converter can help us meet this challenge at minimal cost. The ratiometric delta sigma ADC outputs a quantity that we call the Bilinear amplitude ratio, which is different from the conventional amplitude ratio used in weakly coupled resonator sensors. So we'll see that this Bilinear amplitude ratio has some really nice properties, and in particular with respect to linearity of measurement. And then we will conclude. Frequency-modulated resonance sensors, MEMS sensors, to which I dedicate my research, are mostly used in high-end applications for inertial sensing, pressure sensing, mass or gas sensing. So a frequency-modulated resonance sensor revolves around a MEMS resonator whose mechanical stiffness K changes with epsilon, and epsilon is the quantity we seek to measure. And there are some electronics that sustain the oscillation of the resonator. So as epsilon changes, the oscillation frequency changes, and we can deduce the change in epsilon from the change in oscillation frequency. So the big advantage of this kind of sensing is that frequency is a quasi-digital quantity, so it can be measured at very little cost by counting the zero crossings or the edges and comparing them to a reference oscillator. A disadvantage of this kind of measurement setup, of course, that the stiffness of MEMS resonator is very sensitive to, very dependent on temperature, and it is best to use differential measurement setup where the frequencies of two MEMS oscillators are measured, one which has a positive dependence on epsilon and one which has a negative dependence on epsilon. There has recently emerged an interest for resonance sensors based on so-called weakly coupled resonators. So these sensors consist of two nominally identical resonators with opposite sensitivities to epsilon. The resonators are coupled through a restoring force, for example. This is as was performed by Affiliation and Kraft in the past few years, or through a driving force, which is the approach we tend to favor, and through some sustaining electronics, the resonators are maintained in a steady state of oscillation, as in a conventional oscillator. In such a setup, the oscillation frequency has little dependence on epsilon, but the phase difference between, for example, the motional signals or the ratio of the amplitudes of the motional signals are highly sensitive to epsilon. What makes the amplitude ratio interesting is that it is intrinsically differential, and also that amplitude measurements are not limited by nonlinearity, what is called the AF effect in the context of oscillators, and this is as opposed to phase or frequency measurements. However, the main limitation of the amplitude ratio is that it is essentially an analog quantity, and its conversion to the digital domain is an issue that must be faced, in particular when considering integration. So as an example, this figure depicts the architecture of the mutually injection-locked oscillator MILOs that we have been focusing on these past few years. So you have the two resonators here and some transduction blocks, triangles, and some a digital mixer which enforces the coupling between the resonators. The determining parameter of this architecture is the phase shift theta, which is a compound parameter consisting of the delay of the detection block, the delay of the comparator, and the delay of the actuation block. So depending on the value of this parameter theta, the MILO may not only be used as a PM resonance sensor, but also as an AM resonance sensor, meaning that not only the phase between the two motional signals will change, but also the amplitudes of x1 and x2 with opposite sensitivities to epsilon. Now, the solution which is most commonly used for AM resonance sensors is depicted here. It simply consists in digitizing both motional signals output by the front ends of the resonators. This is done by with two high-resolution ADCs with a sampling frequency which is large enough compared to the natural frequency of the resonators. From the digitized signals, it is then straightforward to extract the amplitude of each signal, so digital demodulation is performed, and then divide one by the other to calculate the amplitude ratio. It should be noted that the relevant information on epsilon, which is contained in the amplitude ratio, is only contained in a narrow bandwidth, which is given by f0 over 2q, q being the quality factor of the resonator. So, and this gives a measure of the required output data rate. So taking this into account, as well as the cost and complexity of integrating two high-resolution, high-frequency analog-to-digital converters, it is worth considering alternative solutions. So the solution we have been investigating consists in first demodulating the two motional signals in the analog domain to recover the narrow bandwidth amplitudes of both signals. Then one may use a single high-resolution ADC with reduced sampling frequency constraints to derive the ratio of the two amplitudes by using, for example, V2 as the reference voltage of the analog-to-digital converter. So this is the ratiometric ADC approach, which may fundamentally be applied with any ADC architecture. And given the high-resolution, small bandwidth requirements, investigating delta sigma ratiometric ADCs makes perfect sense. The ratiometric delta sigma ADC was initially proposed by Ferreira in the context of resonant eddy current displacement sensors. It is depicted here. It outputs a bit stream at the sampling frequency fs, whose average value is equal to this quantity, which we call the bilinear amplitude ratio. While Ferreira fabricated and tested a second-order architecture specifically aimed at a 16 MHz application, we are seeking to develop a ratiometric ADC with better than 16-bit effective number of bits for all amplitude-modulated weakly coupled resonant sensors whose oscillation frequency is smaller than 1 MHz and whose quality factor is greater than 500. In fact, the quality factor sets the oversampling ratio over sigma delta and thereby limits the effective resolution. Now, as mentioned in the previous slide, the quantity which is digitized by the ratiometry sigma delta ADC is not the amplitude ratio R, but a bilinear version of R, as is made clear by this formula here. Still, this output metric serves our purpose well for several reasons. First, irrespective of which weakly coupled resonator is used, it is intrinsically differential, like the amplitude ratio. Moreover, it is bounded between -2 and 2, whereas the amplitude ratio varies between 0 and infinity. And it has some more interesting properties for for more specific architectures. First, for most amplitude-modulated weakly coupled resonator architectures, the bilinear amplitude ratio is an odd function of epsilon, as opposed to the conventional amplitude ratio. And also, as I will show next, it has some outstanding linearity properties for some specific amplitude-modulated MILO architectures. We have represented on the right here the conventional amplitude ratio, that's the blue and green curves, and the bilinear amplitude ratio, the red and black curve, for two MILO architectures, each characterized by system parameter theta. So we can see that the slope at origin of all these curves are equal, which shows that the nominal sensitivities of all these output metrics are equal. And the fact that the bilinear amplitude ratio is more linear than the conventional amplitude ratio is also clearly visible. In fact, a very remarkable result is that the bilinear amplitude ratio is perfectly linear with epsilon in the case of the MILO architecture with theta equal 45 degrees. So this is the red curve. And in the case of theta equal 90 degrees, the black curve, the bilinear amplitude ratio is only linear to second order, but still much better than the conventional amplitude ratio. Of course, the previous results are obtained in a highly idealized framework where the resonators have perfectly identical parameters and all the nonlinearities that may affect MEMS devices are neglected. So to assess the robustness of our results in a more realistic framework, conducted some experiments using actual resonators and electronics, a setup which previous characterizations showed to be full of non-idealities, so mismatched quality factors, nonlinear damping, nonlinear transaction, etc. And the results are shown here. So changing the bias voltage of one resonator lets us change the stiffness mismatch epsilon in a controlled way. And for each value of epsilon, we calculate the conventional amplitude ratio, the blue curve, and the bilinear amplitude ratio, the red curve. And here also the improved linearity of the bilinear amplitude ratio is quite manifest. So to conclude, the bilinear amplitude ratio has some remarkable metrological properties compared to the classical amplitude ratio. So it is linear or has a very improved linearity compared to the conventional amplitude ratio for MILOs. It has improved linearity also for several other amplitude-modulated weakly coupled resonator architectures, and these properties seem to be quite robust with respect to several non-idealities, as we have shown experimentally. So the bilinear amplitude ratio is also very amenable to integration, and the ratiometric delta sigma ADC approach performs conversion and division with a single electronic block. So simulations of this architecture at extracted transistor level show worst case effective number of bits to be greater than 16 bits, and the ASIC is currently has been fabricated and is currently being tested. Thank you for your attention.